Hello to all of you beautiful people and welcome to this organic chemistry worksheet. So I am actually in Thailand right now as I'm busy recording this. So right now I'm in an island called Koh Tao. In the background there are chickens walking around behind me. So if you hear one or two chickens in this worksheet, well, I do apologize. Hope you guys are doing well. So the first thing I want to let you know is that this worksheet is downloadable. So I would suggest that you download the worksheet, and then what you'll be able to do is be able to look at the worksheet and go to the specific section or questions that you would like to practice, and then you can just jump to the specific part in the video where I explain the answer. So maybe you don't want to do number 1 and 2 and 3 and 4, for example, but you want to jump to number 77, for example. So you could look at the worksheet, go to number 77 and be like, that's a question I would like to try. You could then go fast forward in the video to question 77, and you could see exactly how that part is solved. Okay, so just check the description below. There should be a PDF there that you can download. Awesome. So I'm going to break every single question up into a separate slide just so we have more space and it's not too overwhelming. Okay, so welcome once again. Let's get started. With this question, they would like us to identify the homologous series. Now, what is a homologous series? It's quite a weird word, but what it actually means is it's like, what is the family name? So what we've looked at in the past is family names such as alkanes, alkenes, all of these ones, alcohols. I'm not going to go through all of them, but these are all called homologous. By the way, if you are IEB, you guys typically do not do ketones and aldehydes, but you do all the others. Okay? For those of you that are doing CAPS, which is most of you, you guys do ketones and aldehydes. Okay, and then we get a few others like esters, carboxylic acids, haloalkanes, alkynes, all of that. Okay, so they want to know what is this one, and they also want to know what is the general formula. Now, the general formula is the thing that goes like CnH2n plus 2, for example, or CnH2n minus 2, or CnH2n O2. These are called the general formula. So let's start with the homologous. So what I see here is that there is a carbon, and then there's an oxygen randomly in the middle, or not in the middle necessarily, but just somewhere in this main chain over here. Now, the only homologous series that can do that is an ester. An ester, they are the only types of molecules that have an oxygen somewhere in between the carbons. You might be saying, yeah, but Kevin, my bro, what about aldehydes? They also have oxygens somewhere in the main chain. Or what about alcohols? Yeah, okay, so for example, an alcohol does have an OH, or it does have an oxygen. I agree with you. There it is. But what I'm trying to say is that this oxygen is somewhere in the middle, somewhere like in between. So for example, if you get something like this, you see how there's an oxygen somewhere in the actual, it's like somewhere in between the carbons. That's an ester. When it's on the end like that, or even if it's like somewhere over here, that's not what we're talking about here. So when you have an oxygen somewhere in the carbon chain, that is an ester. Now, esters, for their general formula, or let's just quickly say yes, so the homologous, that was an ester. Okay, good. Now we're going to look at the general formula. So what I like to do, because I know you don't want to always have to memorize everything. I mean, you can if you wanted to for the general formula. I don't think it would be that bad. But if you get stuck, then what I would tell you to do is the following. Just look at how many of each thing there are. So there are 4 carbons, okay? Let's look at how many hydrogens. 1, 2, 3, 4, 5, 6, 7, and 8, okay? Let's do that. And then there's 2 oxygens. There's always 2 oxygens for esters. Whether there's 7 carbons or 25 carbons, there will always be 2 oxygens. So what I would then do is just look at these 2 numbers, and I can see that the hydrogen is double the carbon. So what I would then say is that I can just make carbon N. So that means hydrogen would always be double that. So that would be 2N. And then I know that there's always 2 oxygens, no matter what, whether there's 75 carbons or 3 carbons. For esters, this would then be the general formula. So let's go write that out. The general formula would then be CnH2nO2. Okay, that's fantastic. The goal of this question is to identify the homologous series, which, remember, once again, is things like alcohols, alkenes, alkynes, aldehydes, ketones, carboxylic acids. That's what they want for this one. And then they also want to know what is the general formula. The general formula is like things like CnH2n minus 2, or CnH2n, or CnH2n O2, for example. Sorry, that's meant to be an N over there. So that's the general formula. Okay, so if we look at this molecule, we can see that this is a very basic molecule. There are no oxygens, there are no double bonds, there are no triple bonds. So this is the most basic molecule of all. This is the alkanes. So under the homologous, the answer for that one would be alkanes. Now for the general formula, you could memorize this if you wanted to, but if you do want to find a better way to do it, then what I'll show you is the following. Just count how many things there are. So there are 4 carbons. If you count the number of hydrogens, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you might not be able to identify a relationship over there. But what I would show you is the following. For every carbon, there are 2 hydrogens. Can you see it? For every carbon, there are 2 hydrogens. So what I could say then is that, okay, so yeah, first remember that. For every carbon, there are 2 hydrogens. So we could say something like Cn, and then there would be double the amount of hydrogens. Then, on the end, there's 1 extra hydrogen and 1 extra hydrogen. So there will always be 2 extra hydrogens. So we can just say plus 2. So, for example, if we had a molecule that had, for example, 6 carbons, then I'm not going to draw the hydrogens out, but you know they're there, right? So what we could say then is that there would be 1, 2, 3, 4, 5, 6 carbons. And then for every carbon, there would always be 2 hydrogens. You see them? So you could say H12. And then there's always going to be these 2 random ones on the end. So we could just say plus 2, which would then be 14 hydrogens in total. Okay, so Kevin, so what's the answer, my dude? Well, this is the answer over here. We should know that for alkanes, the general formula is going to be CnH2n plus 2. So as I said, you could memorize that if you wanted to, or you could just try to work it out each time. And I think that's a better approach because it really shows that you understand your work. So in this question, we have to identify the homologous series of this molecule as well as the general formula. So with the homologous series, it could be a carboxylic acid, an ester, aldehyde, alkane. So the first thing that I notice is that it has this OH. Okay, now there are different types of molecules that have OHs. We've got carboxylic acids that have OHs. What else? We've got alcohols. Now, we can see that it only has an OH. It doesn't, for example, have a double bond oxygen connected to an OH. If it was like that, then it would be a carboxylic acid. But because we just have that OH over there, this means that this is a alcohol. So for the homologous, we'll say that this is a alcohol. Now, to work out the general formula, as I've said in previous lessons or videos, you can memorize this. However, if you get stuck, what you can do is the following. You can see that there are 1, 2, 3, 4 carbons. Okay, so let's write that down. Then for the hydrogens, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we can say 9. And then there's an OH. Okay, so what we can see that this hydrogen is that it's double this number plus 1. So we could say something like Cn, then the hydrogen will be double that number plus 1, okay? And then you could say OH. And so, as I said, you can memorize that, or you can just try figure it out for each question. Okay, so yeah, hope that one makes sense. For this question, we need to identify the homologous series and the general formula. So for the homologous series, what we can realize is that this one has a halogen. Okay, so this would be a haloalkane. So for the homologous, this one is a haloalkane. Some people say, oh no, let me not mention other names. I don't want to cause any confusion. So that's the homologous. And then for the general formula, you can memorize this or you can try figure it out. I like to try figure it out, or I prefer when students do it like that, because trying to memorize all the different general formulas, I mean, it's not that bad, but when you're in an exam, it can maybe, if you go blank, or you're having like a complete meltdown or like a panic attack, it's not nice to have to remember stuff. Okay, so let's see, there are 3 carbons, so we can try work this out together. So there are 3 carbons, and then there's 1, 2, 3, 4, 5, 6, 7. So there's double the hydrogens plus 1. So we can say sorry, let me just first say that, and then there's a Cl. So if we want to work out the general formula, we could say N over here, and then you could say the hydrogens will be double that, and then plus 1, because that's how you would get to 7. And then there would be some type of haloalkane. Now, it could be Cl, it could be Br for bromine, I for iodine, F for fluorine. So what you've maybe seen in previous lessons with your teacher, your textbook, is that we're not going to put Cl over here. We're rather going to put X. Now, that X represents any haloalkane that they've wanted to use. Okay, so for the general formula, that is what we will say, 2n plus 1, and then x. With this question, we are going to identify the homologous series and the general formula. So for the homologous, that could be alcohols, alkenes, alkynes, alkanes, haloalkanes, esters, it's all of those. So the first thing that you would realize is that it's got a double bond over here with the carbons, and so that should remind you that these are the alkenes, okay, with an E. So let's write that down, Alkene. All right. And then for the general formula, once again, you can memorize this, or you can just try work it out. So for example, if we look at this molecule, there are 4 carbons. Okay. If you had to go count the hydrogens, there would be 1, 2, 3, 4, 5, 6, 7, 8. So what we can see is that there's a double. So we can say CNH. So if there are N carbons, then there would be 2 N hydrogens. So your general is going to be CnH2n. In this lesson, we're going to look at we're going to take this molecule and we're going to identify the homologous and the general formula. So for the homologous, what we can realize is that it's this part here that's a little bit interesting. So by the way, if you are in the IEB curriculum, you guys typically do not look at these types of molecules, which is either the aldehydes or ketones. But if you CAPS, which is most of you who are watching this, then you guys do aldehydes and ketones. So we're going to see that there's a C double bond oxygen. Now we do see that in many molecules. We see that in the carboxylic acids, for example, where you get that, but you also get an OH. So if you see that, that's a carboxylic acid. Now, we also get double bond oxygens in esters, which is like that. But the reason that this is an ester is because there's an oxygen somewhere in between 2 carbons. Okay, so that's an ester. We also see it in these types of molecules. But then if there's a hydrogen over here, then this means that this is the last carbon. So this is the carbon that is on the side. When it's on the side, maybe you've heard me say this before, that makes it an aldehyde. Aldehyde on the side. All right, but if you have a double bond oxygen and the carbon that it is attached to is in between 2 other carbons, then it is a ketone. So that's the answer for this one. The homologous is going to be a ketone. Now we need to work out the general formula. So you can memorize it or we can try figure it out. So I'm going to try figure it out. So there's 3 carbons, 6 hydrogens, and an oxygen. So that's pretty easy. We can say that there would be N carbons, then there should be double the amount of hydrogens, and then there's a random little oxygen on the end. So we can just do it like that. And so that would be your general. So let's just write general formula. And that would be CnH2n with a big capital oxygen. We have to determine the IUPAC name of this molecule. So you should be able to identify that this is an ester because it's got a carbon double bond oxygen. And then what's most important though is it's got an oxygen that is somewhere in between carbons. Now the way to name an ester is there's two parts. There's the alcohol part and the carboxylic acid part. So put a line going there. Okay, and the part that has the double bond oxygen, that's the carboxylic part, because remember, an ester is the combination of a carboxylic acid and then an alcohol, so this would be the alcohol part. So for the alcohol part, it's got 1, 2, 3, so that's prop. Remember, 3 means prop, but then you're going to say propyl, okay, and then the carboxylic acid part is 2, so that's eth. Have a little space over here. That's eth. But now that's not the name. It's not propyl eth. That sounds weird, right? Esters always end with anoate. So we're going to say anoate. So the name of this molecule is propyl ethanoate or propyl ethanoate, whatever you're comfortable with. We need to determine the IUPAC name of this molecule. So the first step is to work out the longest carbon chain. So you could go 1, 2, 3, 4. Some of you might have gone 1, 2, 3, 4. By the way, the longest continuous chain is when you can draw the line without lifting up your pen. Okay, so 1, 2, 3, 4. That's one of them, or 1, 2, 3, 4. So whichever way you go, 4 is the longest we could ever make. So I would start the naming with that. So 4 means bute. Okay, now let's look at the branches. So I'm going to just do this one over here. So, if we name it from the left-hand side, then the branch would be this one over here. And that would be on carbon number 2. If you had to name it from the right-hand side, this would not be correct. Because then that would be carbon 1, that would be carbon 2, that would be carbon 3, and that would be carbon 4. So your branch would be on carbon number 3, right? And the goal is to keep the branch numbers as low as possible with these types of alkanes. So we're going to name it from this side. Okay, so on carbon number 2, there is a 1 carbon branch. Now 1 means meth. Because it's a branch, you're going to say YL. Now, what type of molecule is this? Is this an alcohol, an ester, a carboxylic acid, an aldehyde, a ketone, a alkane, alkene? What is it? Well, there's only carbons and hydrogens, so it's either going to be an alkane, alkyne, or alkene. There are only single bonds, so this is an alkane. So the name of an alkane just ends with A-N-E. So that is the name, 2-methyl or methyl butane. Whenever there is a number and a word, we always separate it with a hyphen. So here we have to work out the IUPAC name. So the first step is just to work out the longest carbon chain. So for example, we could go 1, 2, 3, 4, 5, 6, 7, 8. Let's see if we can do better. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the longest. The longest chain is the one that you can make without having to lift your finger from your paper, or lift your pen from your paper. So with 9, then we're going to say non. Okay, they don't usually go up to 9 and 10, but yeah, I thought I'll just add it for this one. Usually they go up to 8, which is oct. Now, we need to decide whether we are going to name this molecule from this side or from over here. Now, you can't just choose whatever you feel like. There's actually a specific way we determine this. If you had to start on this side, then this would be carbon 1, 2, 3, 4, 5, 6, 7, 8, and 9. If we did it like that, then the branches would be on carbon number 6 and carbon number 7. Now, if we rather had to name it from the left-hand side instead, or the left part, then this would be carbon 1, carbon 2, 3, 4, 5, 6, 7, 8, 9. So now your branches are on carbon 3 and carbon 4. So because of that, the lower numbers, we are rather going to choose that. So let's see what branches we have. So on carbon 3, it's a 1 carbon branch, and on carbon 4, it's also a 1 carbon branch. So 1 means meth. So the way we'll do this is we'll say that on carbon 3 and on carbon 4, there is a methyl, like that. And then because there's 2 of them, you're going to have to add the word dimethyl. And then what type of molecule is this? Is it an alcohol, ester, carboxylic acid, alkane, alkene, alkyne, haloalkane? What is it? Well, there's only carbon and hydrogen, and there's only single bonds. So that's an alkane. Alkanes end in the word A-N-E. So that is the name of this molecule. For this molecule, we need to come up with the IUPAC name. Okay, so step 1, find the longest continuous chain. So I think that's just going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's the longest. So that would be oct. You might say, yeah, but what if we go 1, 2, 3, 4, 5, 6, 7? You see, that's only going to give us 7. Okay, so that's oct. Now we need to decide whether we should name it from the left or from the right. We are definitely going to choose the right because we are trying to make the branch numbers as low as possible. So if you look carefully, there is a branch over here, okay? And then there's also a branch over here, and then there's another branch over here. So the branch is on carbon number 2 and also on carbon number 3. Now, many learners make the mistake of saying that this part over here is a ethyl. The reason that they do that is they say, oh, look, there's 1 carbon and 2 carbons. 2 means eth, but that is not correct. You need to look at each branch. So look at this branch. That's only 1 carbon. That's meth. Look at this one. That's only 1 carbon. That's meth. If it was something like this, where there was that, then if you look at this branch over here, that is 2 carbons. Okay, so there's a difference. You need to make sure that you understand that. Okay, and then this branch is chloro, for chlorine. So we have to use the alphabet. So C always comes before M. So we'll start with chloro. So chloro is on carbon number 2, so we'll say 2 hyphen chloro. Then, I'm going to just move that up a little bit. Then on carbon number 3, there are 2 branches. So we'll say 3, 3, and then you're going to say that that is a methyl. Okay, let me just write that a bit better. Methyl. But because there's 2 of them, you're going to say di. Like that. And then this molecule is a haloalkane because it's got a halogen. So this is a haloalkane. Haloalkanes end with ane, just like alkanes do. So that is the name of this. 2-chloro 3,3 dimethyl octane. Here we have to give the IUPAC name. So step 1, find the longest chain. So that's going to be 1, 2, 3, 4, 5. 5 means pent. Okay. Now, is there a functional group? Yes, here it is. That is your functional group. So you are going to start naming from the side that is closest to the functional group. It doesn't matter where the branches are. You are going to start at the closest side to the functional group. So we're going to start here. So that'll be carbon 1, that'll be carbon 2, that'll be carbon 3, 4, and 5. So here is a branch. So that's on carbon number 3. How many carbons are in that branch? 1. So that's meth. Okay, let me just move this up. It's one word over here. Methyl pent. Oh, let me write that a bit better. Methyl pent. Okay, now this is an alkene. So the way that you would end this now is you would say that on carbon number 1, there is a double bond. Like that. So 3-methyl pent, 1-ene. Here we need to give the IUPAC name. So step 1, find the longest continuous chain. So 1, 2, 3, 4, 5, 6. That's the longest you would be able to find. 6 means hex. Now let's look at the functional group. Where is the functional group? Well, the functional group is here by this OH. That means we need to start naming the molecule from the right-hand side, because that would give us, or that is the closest place to the functional group. Some of you might be like, yeah, but Kevin, shouldn't we start on this side because the branch is closer? Remember, it is not about the branch numbers. Only if we were dealing with alkanes or haloalkanes, for example. But for all the other molecules, you start naming on the side that is closest to the functional group. So this will be carbon 1, 2, 3, 4, 5, and 6. Okay, so on carbon number, so where are the branches? Well, this is a branch because here's the continuous chain. And so everything that sticks out, that's a branch. So that's on carbon number 4. So we can say 4 hyphen. Now, how many carbons are in that branch? There's only one, so that's meth. So you're going to say methyl, like that. And then the functional group. So the functional group is on carbon number 3. So how do we do this? So some students, they get a bit confused with, should we put an AN over here or shouldn't we? And we actually should, and the way that I help learners to remember that is to ask them, what is the most common, what is the type of alcohol that we use in alcoholic beverages? Well, that's ethanol. Okay, so that's ethanol. So if you write out the word ethanol, you can see that there is an AN over there. So we're going to say hexane, okay, and then it's on carbon number 3, and it's an alcohol. So that's OL. So you wouldn't say 4-methyl hex 3. You must put the AN, okay? Just like you do in ethanol. So the final answer would be 4-methyl hexane 3-ol. So for this molecule, we need to give the IUPAC name. So step 1, find the longest continuous chain. Now, a lot of you are going to go 1, 2, 3, 4. But what if you had to start over here? Or what if you had to start over here and go like this? Whoa, look at that. 5 carbons, okay? That is the longest that you would find. You're not going to be able to find longer. Okay, so that's going to be 5 carbons. So 5 means pent. Okay, now we need to look at branches. So branches are the things that are sticking out. So this is 1, and this would be another. Okay, so we have that's a 1 carbon, so that's methyl. Then we have a chlorine, so that's chloro. Okay, now the idea is that you want the branch numbers to be as low as possible. So if we start naming from this side, 1, 2, 3, 4, 5, then, okay, so then your branches would be on carbon number 2 and carbon number 3. If you had to start labeling it on the other side, then it would be at number 1, what is this, 3, 4, and 5. So then your branches would be on carbon number 3 and 4. So you would not do it that way because you want the numbers to be as low as possible. So we are going to name it from this side here. So that's 1, 2, 3, 4, 5. Now, you have to go alphabetically. So C is before M. So you are going to say that on carbon number 2, there is a chloro. And then on carbon number 3, there is a methyl. Okay. And then how many carbons did we say? 5. So that's pent. Now, this is a haloalkane because it's got the halogen. Haloalkanes just have the same ending as a normal alkane. And so that is the name. 2-chloro, 3-methyl pentane. So here we need to come up with the IUPAC name. So the first step is just to make sure we see the longest carbon chains. That would be 1, 2, 3, 4. Okay, so 4 means bute. Okay, now if we start, we're going to start, this is the functional group. Okay, so you're going to start naming from the side that is closest to the functional group. So this is number 1, number 2, number 3, and number 4. So on carbon number 2, you see there's a branch over here. How many carbons are in that branch? 1. So that's meth. So you say that on carbon 2, there is a methyl branch. Okay, we need to make this one word. Okay. Now we need to think about what type of molecule is this. Like, is it an alcohol, alkene, ester? Well, what you should identify is that it's got the O, double bond O, with the OH. That is a carboxylic acid. Carboxylic acids, how do we end the name? Well, think about the most common one, like vinegar. Ethanoic acid. So that is how the name ends. You just say anoic acid. you don't have to say which carbon the functional group is on, because on carboxylic acids, it is always on carbon number 1. And so this would be the name, 2-methyl-butanoic acid. We have to provide the IUPAC name of this molecule. But what makes this quite interesting is that we've been given the condensed formula. Now, I would not recommend that you try to name it by simply looking at that, okay? I've been teaching for many years, and I see that students do struggle with that. I even struggle with that. I always try to draw out the structural formula first. So the way I do is I start from the left. So I see there's a CH3, so I know that that's going to look like this. Okay, then there's a CH2, so that's just going to be like that. Okay, so we've done that. Then there's a H, a C, and a CH3. So some students ask me, they're like, Kevin, does that mean it's part of the main part, or does this bracket mean that it's part of does it mean that it's a branch? Now, there's no rule that tells us whether it's a branch or part of the main part, but it's very easy to tell. It cannot be part of the main part, because how would you fit a CH3 over here? You see, it is impossible. That's only a CH2. We cannot put another H over there, because then these parts wouldn't be able to fit in. So it cannot be a CH3 in the main part. So what that means then is that it's a branch. Okay? So what we see then is that there's a H, a C, and a CH3. So that would look like this. And then down here you could put a CH3. You see? So there is, let me show you exactly what we did here. So this C is that C. This H is that H. And then this CH3 is that CH3 over there. Okay, bit of an interesting part that, but yeah, I'm sure that's, if you just look at that a few times, you'll understand what we've done there. Okay, so we've done that. The next part's easy, CH2, so it's just a C with 2 H's, so that's part of the main chain. The next part is also easy, it's a CH2, so that's just part of the main chain. And then the next part is the ending, so that could be a CH3 because that ending has a CH3 like that. Okay, now we have to give the name. So that's just the structural formula, but now we need the name. So the longest chain would be 1, 2, 3, 4, 5, 6 carbons, so that's hex. We're going to name it from the left-hand side, which is this side over here, because the branch, which is this one, is we want the branch to be closest to we want the branch number to be as low as possible. So we can say that this is carbon number 1, this is carbon number 2, and this is carbon number 3. In this branch, there is 1 carbon, so that's meth. So we can say methyl because it's a branch. So we can say that on carbon 3 there is a methyl, and then this whole molecule, is it an alkene, alkyne, alkane, carboxylic acid? Well, it's an alkane. So you end an alkane with just naming it, like that. So there is the final answer. We have to determine the IUPAC name of this molecule, but it's been given in condensed formula. So I would suggest that we first expand it. So I just start on the left-hand side. I don't look at any of this. I just look at the first part. So that's a CH3. So that goes like this. Okay. Now the next part. Students often ask me, like, how do we know if this is a branch or if this is part of the main carbon chain? Well, there's no exact rule whether the brackets is a branch or a part of the main chain, but it's always easy to figure out. Okay, so let's try to see what happens here. They tell us there's a carbon, okay, and then there's 2 CH3s. So there's a carbon, and then you might think, oh, well, then there's 2 CH3s. Over here, but how would you fit 2 CH3s? You can't do that because then you wouldn't be able to add another one. So that CH3 is definitely not part of this main chain. But what we could rather do is we could go this way and then this way, because now you can easily make a 3 H's on each of those. And there, you see what we've done? We've just added a CH3 there, and we've added a CH3 over there, so we've just added 2 CH3s. If you tried to add it in any other way, you would realize that you're going to get stuck. So it becomes quite easy to figure out whether it's a part of the main chain or whether it's part of a branch, okay? So we've done this part, we've done that part, we've done that part. Now the next part says that there's 2 CH2s. Now CH2s are easy because they are part of the main chain, because there you can put a C with 2 H's, and then you can just add another one, a C with 2 H's. So you've added 2 CH2s. You see what I mean? That's a CH2, and that's a CH2. So we just added 2 of them. And then the last part is just a CH3, which is just showing us that that's the end, because it's easy to put in a CH3 at the end like that. Okay, so now we have to name this molecule. So the longest carbon chain would be 1, 2, 3, 4, 5 carbons. So 5 means pent. Now on carbon, we're going to name it from the left-hand side because the branches are over here, or is over here, and over here. So we're going to label it from the left-hand side. So we could say that that's on carbon number 2, but then there's another one as well. There's one here, and there's one here. And then you can say methyl. Now some of you are like, so, shouldn't we put di? Of course. I was just filling in the basics first. So because there's 2 of them, we say dimethyl. And then this whole molecule, what is it? Is it an alcohol, ester, carboxylic acid? It's an alkane. So you end the name with ANE. So there's the answer. 2,2 dimethyl pentane. We need to find the IUPAC name of this molecule. So because it's given in condensed formula, let's quickly go expand it a little bit. So I just start on the left-hand side. So the first one is a CH3. So a CH3 would just look like that. Okay. Then they say there's a CH. Okay, and then another CH. Okay, so that's quite weird. So that's a CH and then another CH. Okay, so there's probably going to be like a double bond or a triple bond maybe, just to fix everything up over there. But don't worry, we'll come back to that. Then there is a C connected to a BR and an H. So that would be like something like that. And then there's a CH3. Okay, now notice that this carbon and this carbon only have 3 bonds. So we can fix that by putting a double bond. Sometimes they'll actually show you the double bond over there. They'll do something like this. They'll say CH, CH. That is sometimes shown in certain textbooks. So your teacher might do it like that. But they also sometimes show it like that without showing the double bond. Okay, so there we go. Now we need to come up with the name for this thing. So we're going to label it from the left. The reason is that the functional group is this double bond. So we're going to label it from the side that gives the functional group its lowest number. So the longest continuous chain would be 1, 2, 3, 4, 5. So that's 5 carbons. So that's going to be pent. Okay. Then the branches would be the bromine. So that's on carbon 1, 2, 3, 4. So that's going to be on carbon 4. There is a bromo. Okay. And then for pentene, or sorry, for alkenes is what I was trying to say. We'll say that on carbon number 2, there is a double bond. So 4 bromo, pent, 2 ene. Have a look at this one. So I know that this looks intimidating, but I'll show you, it's pretty straightforward. So we need to find the IUPAC name, so just scratch all of that out. Just start on the left-hand side. So it's CH3. Okay, so we can scratch that out. Then there's a CH and another CH. So that's usually a double bond. As you practice this, you'll get used to this. Okay, so we've done that. Then there's a CH again. Okay. Now look at the CH3. Now some students, they don't know whether that goes part of the main chain, like going this way, or whether it becomes a branch going that way. Now, let's assume that we would like to keep the main chain going in this direction. Okay. And everything else is a branch. I'm going to try to show you that a CH3 cannot fit over here. Because if you try to put a CH3, there we've done it, but then you've just ended your chain, and so you cannot add any more things, because you cannot add a carbon to a hydrogen like that. So then what I'd rather tell you to do is to make that CH3 a branch. See, because then you can easily fit it in, and you can still carry on with the rest of your chain going that way. Okay, makes sense? Good. So that part is now done. Okay, and that part's done. Okay, the next part is a CH. Now, whenever you see that, it's just a C with an H like that. Now, here, once again, we've got a bracket where we need to decide if it's going to go part of our main chain or whether it's a branch, because it can be both. I mean, it could be one or the other, okay? So I'm going to try to show you that it cannot be part of the main chain that goes this way, because if it was, let's say it was, then you would have a CH2. That seems okay. And then you would have a CH3. But now look what we've done. We've just ended our chain, and so you would never be able to add this stuff on over here. So then we'd go back, and we'd rather make it a branch. So we would rather go down, and we could say CH2, not a problem, very easy, and then CH3, just like that. And so now we can still carry on with the main chain. So we're done up to there now. Now, CH2. There's two of them, so we could definitely add this in the main chain because there's CH2, and then you can easily just add another one. You see how we're not ending the chain? So that works nicely. So sometimes the bracket is a branch, and sometimes the bracket is part of the main chain, and as you practice this, you'll begin to realize it's actually pretty easy to tell which one it is, and then the next part is a CH3. Okay, now, you see we're done there. So you see here there's only 3 things surrounding this carbon and 3 things surrounding this carbon. So to fix that, you make a double bond. Now, sometimes they will tell you that there's a double bond by doing something like this. They'll say CH double bond CH. Maybe you've seen your textbook do it like that, or your teachers. So sometimes they show it like that, sometimes they don't. Now, we need to come up with the name of this huge molecule. So this is our main chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons. Okay, so 8 means oct. Now, we have to label it from the left because the functional group is over here, and you always label from the side that is closest to the functional group. So, okay, so that means that this is carbon number 1, 2, 3, 4, 5, 6, 7, and 8. So on carbon 4, there is a methyl. On carbon 5, there is a ethyl. Okay, so E comes before M in the alphabet, by the way. So you're going to say 5 first. Many students are like, yeah, but shouldn't we say 4 first because 4 comes before 5? Yep, but we're not looking at that. We're looking at the alphabet. So E comes before M. So we're going to say 5 ethyl, then 4 methyl. I'm going to run out of space. Methyl. And then we have oct. Now, this is a double bond. So we're going to say on carbon number 2, there is a double bond. And that would be the name of this one. So that's quite a good one. Give the IUPAC name of the following. So don't worry about all of this. Just start expanding it slowly so we can see what this thing actually looks like. Okay, so CH3 is the first part. Then the next part, they tell us that there is a carbon. Okay, and then there's 2 CH3s. So some students, they don't know whether that should go over here or whether they are branches. Now, I'm going to try to show you that they are going to be branches and they're not going to be part of the main chain. Let's say our main chain goes like this, just to keep everything nice and simple. Okay, now if they were part of the main chain, you would have said CH3. But now you see, we're pretty stuck. Like, how are you going to add the second one? You can't add onto a hydrogen. So for that reason, they are not part of the main chain. Instead, they are branches. So you could rather do that and then easily put the 3 hydrogens in. Like that. Okay, and so there we've done up to this part. Now there's a CH2. That's an easy one. CH2. That's part of the main chain because you can easily add on to that. The next part is a CH. So we can say CH. And then there's this part over here now, which once again cannot be part of the main chain. Well, I'll show you what I mean. So you can't add 2 of these next to each other. Let me show you why. So let's say you try to add the first one, CH2, and then CH3. So that looks okay. But you wouldn't be able to add the second one to that because this is a hydrogen. But what you could do is just add it down here, CH2, and then CH3. You see, so what we just did is to this carbon over here, which is this one, we just added two CH2CH3s. CH2CH3, there's the first one, CH2CH3, and here's another CH2CH3. Okay, so now we need to name this molecule. So we need to find the longest continuous chain. So let's try this. 1, 2, 3, 4, 5, 6. Can we do more than 6? I'm not sure. Let's try 1, 2, 3, 4, 5, 6. No, that's also 6. 1, 2, 3, 4, 5, 6. Okay, so I think 6 is the best weight. 1, 2, 3, 4, 5, 6. Yeah, you're not going to get more than 6. So because of that, I'm just going to use that as the main one because that's the easiest to work with. And then everything else that is coming off that is the branch. So that's a branch. That's a branch, and that's a branch. We will start labeling from the left because that'll give us the lowest branch numbers. So that means this would be carbon 1, this would be carbon 2, 3, 4, 5, and 6. Okay, so on carbon 2, there is 2 methyl branches. So let's just write that in, methyl and methyl. On carbon 4, there's 2 carbons in that branch, so that's an ethyl branch. Okay, so it's got 6 carbons. 6 means hex. Now for the labeling of the branches, it has to be alphabetical. So E comes before M. So we'll start with carbon number 4, because that's carbon number 4, and we'll say that carbon number 4 has an ethyl. Okay, and then carbon number 2, we're going to do that twice because there's 2 of them. We're going to say di, because there's 2 of them, methyl. Whoops, I've run out of space there. Okay, and then we said hex. Now, what type of molecule is this? Well, it's an alkane. It doesn't have any fancy double bonds or halogens. It's just it's just an alkane, so you just end the name like that. We need to find the IUPAC name of this molecule, so we need to expand everything first. So don't worry about all of this. Just scratch that out. So that's going to be CH3. So you just say CH3 like that. Then the next part is a C. Okay. Now there's a CH3 in brackets. Now some learners, they're going to be like, okay, does that mean we just carry on with the main chain? Let's say that our main chain is going to go in this. We're going to just keep going in this direction, okay? So it's not part of the main chain, because if you had to add a CH3 like this, then you have a little bit of a problem, because this carbon would be empty, and you wouldn't be able to add anything onto your, you wouldn't be able to add any of this onto your, to continue, because this H would be blocking the way. So what we'd rather do is consider this CH3 as a branch. So you could go this way. You could have gone up as well. Okay, so we've done that, Then there's a CH, okay, so CH, and then there is another C, okay, and then there's a CH2, CH3. Now, once again, that is going to be a branch, because if you had to try add a CH2, CH3, then you've just blocked the end of your chain, so you wouldn't be able to add any of this on. So instead, let's rewind that and add it down here. And you could have gone upwards as well. Okay, and then there's an H, so we can just add that up there. Then there's a CH2. That's an easy one. CH2, that's always going to just be part of your main chain. Then there's a CH, okay. And then a CH2. CH2. Okay, now, if you look over here, this carbon and this carbon only have 3 bonds surrounding. So we're going to put a double bond there to fix that up. Then if you look over here, we have the same problem happening where you've only got 3 things. So you just put a double bond over there. And so now we need to come up with the name of this. So we know that this is an alkene. So if we're to label it from the left, this would be carbon 1, 2, 3, 4, 5, 6, 7. Okay, so your double bond would be on carbon 2 and carbon 6. However, if we rather, so just remember 2 and 6, if we rather label it from the right-hand side, then your double bonds would be on carbon number 1 and carbon number 5. We would rather choose that because we want the lowest numbers possible. That's the IUPAC rule, right? So we're going to label from the right-hand side. Oh, I don't know why I'm scratching those numbers out. So that's carbon number 1, 2, 3, 4, 5, 6, and 7. So the longest carbon chain is 7, so that's hept. Then the branches would be this one over here. So that's a 2-carbon branch, so that's called an ethyl branch. Then this is a 1-carbon branch, so that's a methyl. Now you have to use the alphabet. So E is before M. E is before M. So we could say on carbon number 4, there is an ethyl. On carbon number 6, there is a methyl. And then, now this is going to be a diene because there's 2 enes. So what's weird about that is that you have to add an A first. You don't just say hept, you have to say hepta. And then on carbon number 1, as well as on carbon number 5, there is a double bond. So there's an ene. But because there's 2 of them, we say diene. And that's pretty much what I'm doing right now, sitting in this bungalow in Thailand. It's so hot and I'm sweating like crazy. So it feels like I'm diene. Haha, that was a good one. Give the IUPAC name. Okay, so always try to see what it looks like first. So scratch all of that out. The first part is a CH3. Okay. Then there's a CH2. That's always an easy one. That just goes like that and like that. Then there's a C and another C and another C. But this one is a CH2. So that's CH2. Okay. Then there's another CH2, which is this one. And then there's a CH3. Okay, now over here there is a bit of a problem, so we're going to fix that by putting a triple bond, because now each carbon is surrounded by 4 bonds. Alright, so that was it. So now we're going to come up with the name. So the longest chain would be 1, 2, 3, 4, 5, 6, 7, which is hept. Now there are no branches, but this is an alkane, so on carbon number 1, 2, 3, there is a triple bond. And so that would be the name of this one. And so that would be the name of this one. Draw the following molecule. Now drawing molecules is easy. You start with this last part just to see hex. That means 6. So you draw 6 carbons. Don't put any hydrogens on them just yet. There we go. Now we look at and let's just say this is carbon 1. This is carbon 6. On carbon 3, there is an ethyl. Ethyl means 2, so you go and put 2 carbons. On carbon 2, there is a methyl. That means 1, so go put 1 carbon. You could have put it up here as well if you wanted to. And that's it. Now just go fill in hydrogens everywhere else. So you always want to make sure that each carbon is surrounded by 4 bonds. Okay? So sometimes there will be double bonds. Not for this molecule, because we know that this is an alkane, so there's only single bonds. There we go. Make sure all the carbons are surrounded by 4 bonds, and that's how it would look. Draw the following molecule. So oct means 8, so just go draw 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's just say that this is carbon 1 and this is carbon 8. You can do it the other way if you wanted to. On carbon number 3, there's a chloro. On carbon number 4, there is a methyl, which is a 1-carbon branch. And then just go fill in hydrogens everywhere else, making sure that each carbon is surrounded by 4 bonds. We know that it's an alkane, so there's no double bonds anyway. Now, if you decided that carbon 1 was this one over here, then your structure would just be the other way around. So you would have a Cl on this one, and you would have a CH3 on this one. Okay, it doesn't matter, it's the same thing. Draw the following molecule. Okay, so this is pent, so that means 5 carbons. Now, you can choose this to be carbon number 1, or you can choose this to be number 1. It doesn't really matter. For this one, I'm actually just going to choose this as carbon number 1, and this would then be carbon number 5. On carbon number 2, which would then mean this one for me, whereas if you started labeling from the other side, you would do it over here. Both methods are perfectly correct. So there's going to be an OH on carbon number 2, so you could do it like that. You could have also done it below, it doesn't matter. And then on carbon number 3, there's going to be a methyl. So let's say like that. Then the rest is just to go fill in hydrogens wherever we can see a space, so that each carbon is surrounded by 4 bonds. Now once again, you could have started on the left hand side, okay? You are allowed to do that as well. Draw the following molecule. Okay, this is butanoic acid, so that means 4 carbons. Then butanoic acid is a carboxylic acid, so you could put a double bond oxygen and then an OH. You could have done it on this carbon as well. That could also be your carbon number 1. The rest of it is just going to be putting hydrogen. There we go. Draw the following molecule. So oct means 8. So let's go 8 carbons. Now you can start labeling on the left. That would be carbon 1. Or you could let carbon 1 be on the right. It doesn't matter. I'm just going to let the left side be carbon 1 and carbon 8 would be over there. On carbon number 2 there's a double bond. On carbon number 3 there is a methyl. Now you could go down or up. Doesn't matter. Now we're just going to go fill in hydrogens wherever we can, so that every single carbon is surrounded by 4 bonds. And so this one still needs a hydrogen. Now look out over here. This carbon here already has 1, 2, 3, 4 bonds. So you're not going to go and add a hydrogen over here, because then there would be 5 things. Okay? There we go. So if you have to draw ethyl propanoate, you need to understand that that is an ester. So an ester is an alcohol and a carboxylic acid. So the first part is always the alcohol. The second part is the carboxylic. So for the alcohol part, it's 2 carbons. That's what eth stands for. Then there's always going to be an oxygen. And then the carboxylic acid is 3 carbons. The first part of the carboxylic would always have the double bond oxygen, so that you get the ester like that. Okay? So don't go put like a double bond oxygen over there, because then it's not an ester. It has to be 1 unit over there. The rest is pretty straightforward. You just go make sure hydrogens are surrounding all the carbons, so that every carbon has 4 bonds. Notice that this carbon over here already has 1, 2, 3, 4 bonds. So you wouldn't need to do anything else. And then there, and then over here. We need to be able to look at these 2 molecules and to determine what type of isomerism is shown. Now remember, isomers are molecules that have the same amount of every element. So they have the same amount of carbon. Look at this, 1, 2, 3. So this one also has 1, 2, 3. If you had to go count, the number of hydrogens are the same, the number of oxygens are the same. They have the same amount of everything. So these are isomers. But you get different types of isomers. You get chain, position, and functional. Okay, if it's functional, then the homologous groups are different. So like, so we could say here homologous is different. So like the one might be a carboxylic acid, and the other one might be an ester, for example. Okay, so if we look at this molecule here, we should be able to identify that this is a ketone. If you look at this one over here, it's got the carbon double bond oxygen on the side, which means it's on the very last carbon, which means it's an aldehyde. Aldehyde has the double bond oxygen on the side. Aldehyde, side. So because the homologous groups are different, this is definitely going to be functional isomerism. We need to determine the type of isomerism shown over here. So remember that isomers are molecules that have the same amount of each element. So on the left we can see there are four carbons. On the right there are 4 carbons. There would be 10 hydrogens on the left, and if you had to go count, there would be 10 hydrogens on the right. So these are isomers. Now you get different types: chain, positional, functional. So if we're to look at the main, let's quickly cross out functional. Functional will only be if the homologous groups are different. So like you have an aldehyde and a ketone, or a carboxylic acid and an ester. But if you look at this molecule, this is an alkane. If you look at this molecule, this is an alkane. So it cannot be functional. Because it's not functional, or because so it's not functional, so it could either be positional or chain. So if we look at the main chain, if you look here, this one has 1, 2, 3, 4 carbons in the main chain. This one has 1, 2, 3 in the main chain. So because the chain is different, the chain is like the backbone, okay? This one, the longest is 4, which would be bute. This one, the longest that you'd ever be able to make is 3, so that's prop. So you see that that's different. So this would be chain isomerism. Okay, so the answer is chain. We need to determine the type of isomerism that we can see here. So if you look on the left-hand side, there would be 4 carbons, 1, 2, 3, 4. If you look on the right, there would also be 4. If you look on the left, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. On the left, there's 1, 2, 3, on the right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's 1 oxygen and 1 oxygen. So that is what isomers are. Isomers have the same amount of elements, or the same amount of each element, okay? So they would have, so that's an isomer, but now you get different types of isomers. So let's quickly try work out what this is. So this is a alcohol, right? Because it's got that OH, and it doesn't have like a double bond oxygen or anything like that. This one is also an alcohol. Okay, so that means it cannot be functional, because functional is when the molecules are different, like the one is an aldehyde and the other one's a ketone, or the one's a carboxylic acid and the other one's an ester. Now, chain, let's see. The longest chain I could make here is 1, 2, 3, 4. This one is 1, 2, 3, 4. So that's the same, so it cannot be that either. So it would have to be position. Now, let's just check. If we look at this one, the OH is on carbon number 1, 2. So you see the OH is on carbon number 2. So the functional group is on carbon number 2. For this one, the OH is on carbon number 1. So you see that the functional group is on a different position. So this is what we call position isomerism. So we're going to say positional. That's the answer. We need to determine the type of isomerism that we can see. So first of all, let's talk about what isomers are. So if you look on the left, there would be 1, 2, 3, 4, 5, 6 carbons. On the right-hand side, there's 1, 2, 3, 4, 5, 6. Okay, so that's the same. If you had to go count all the hydrogens over here, you would get 14. And if you had to go do the same over here, you would also get 14. So that is what isomers are. Isomers are molecules that have the same amount of each element, okay? But they're different. They're either different based upon the different chain, different position, or different functional groups. So let's see. What is this? Is this an alcohol? Carboxylic acid? Well, no, this is just an alkane. And then this one on the right is also an alkane. So because those two are the same, they have the same functional group, so it cannot be that one, okay? We're looking for something that's different. If you look at the main chain, this one is 1, 2, 3, 4, 5, 6. This one is 1, 2, 3, 4 for the longest chain. So that's different. So that's the answer. This is going to be chain isomerism. So here we have a table, and from that table we need to be able to answer some of these questions. So the first question is find chain isomers. So we need to find all chain isomers. So let's first talk about what isomers are. So isomers, for example, would be something like this. Let's quickly make an example. Okay, so there's one molecule, and then here's the next one. All these hydrogens. Don't you just love drawing out hydrogens all day? Okay, so if you had to go look at this molecule, if you had to go count all the carbon, there would be 1, 2, 3, 4, so 4 carbons, and then there would be 10 hydrogens. Don't believe me? You can go check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if you had to look at the bottom, it would be exactly the same. So that's what isomers are. Isomers have the same amount of each element. However, there's different arrangements which would then either be classified as chain, functional, or positional. But we've spoken about this before, right? So I'm not going to go into the deep theory of that now. This is more just practice. So what I think we should do is let's just start with molecule A and just see how many carbons it has. 1, 2, 3, 4, 5. Now let's quickly go see if there's any other molecule that has 5 carbons, because otherwise we're wasting our time, because we know that with isomers they have to have the same amount of everything. So let's just check the carbons. Now this here is an ester. That's methyl, so that's 1 carbon, and then ethanoate, so that's going to have 3 carbons altogether. This one here is going to have 3 carbons. This one's going to have 3 carbons. This is prop, so that's 3 carbons. This one has 1, 2, 3, 4 carbons. This one has 1, 2, 3, 4, 5. Actually, I've got a little idea, guys. Let's just go work out everything. So this one's going to have a total of 12 hydrogens. You can go check that out. Methyl ethanoate. Okay, so methyl ethanoate, that's an ester. So you could go draw this out. You could go draw out methyl ethanoate, which would look something like that. And if you had to go fill that all in, you'd realize that it's going to have 3 carbons, 6 hydrogens, and then 2 oxygens. Okay, this might take a while, but I mean, this is probably the best way. So then, and then this one here has 1, 2, 3, 4, 5, 6 hydrogens, and then 2 oxygens. You see, later on we might be able to look at these ones. Okay, okay, so let's quickly have a look here. This one's going to have 6 hydrogens and then 1 oxygen. Propanal, so that's an aldehyde, so that's going to have 3 carbons where the double bond oxygen is on the side because it's an aldehyde. Okay, I know this may be a little fast for some of you, but yeah, I'm just trying to, you could pause and you could just try to go work out all the structural formulas for each one. So this one would be C3, 6 H's and O. Look at that, you see, so that's going to be something later as well. Okay, now this one over here at G is 5 carbon. Hydrogens would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then oxygen, there's 1. Okay. This one here, H, has 1, 2, 3, 4, 5. This is a nice one. This has got 12 hydrogens. Now this is an alcohol with 4 carbons. So 1, 2, 3, because it says butan. And then on carbon number 2, there is an OH. Okay, and then the rest is all hydrogen. Okay, so it's going to have 4 carbons, 10 hydrogens, and an oxygen. This molecule here, J, 4 carbons and 10 hydrogens. This one at K is a carboxylic acid. You see how it has the CO and the OH? That's a carboxylic. It's got 1, 2, 3, 4 carbons. 3, 4, 5, 6, 7, 8 hydrogens, 2 oxygens. Pentanoic acid, that is a carboxylic acid with 5 carbons. And then let's put the double bond oxygen OH over here. And then each of these are hydrogens. Okay, so this one's going to have 5 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 2 oxygens. Okay, now this is going to make our life a little bit easier to just try to figure out chain isomers, because isomers have to be the same. So what I can do now is I can see C5H12. Here's another one. Any others? Okay, so they will likely, they could be a candidate. Then C3H6O2. Is there any other? Yes, there. That's it. Then C3H6O is those ones over there. Okay, I just randomly stopped with this one. It's quite weird. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen. And then an oxygen. Okay, so C4H10O. So C4H10O could be there. And that's about it. I can't see any others that are the same. Maybe I'm missing something. Let's just double check. C4. Okay, no, that's all fine. Yeah, we did that one. Okay. Yeah, that looks okay. So now it's easier to see which ones are chain isomers because they have to have the same amount of everything. So let's look, for example, at these two. Let's see if they are chain isomers. Well, they actually are going to be chain isomers because if you look at this one, its longest chain is 1, 2, 3, 4. If you look at this one, its longest chain is 1, 2, 3, 4, 5. So those are going to be chain isomers. That would be A and H. Okay, so they are together. Methyl ethanoate and this one. No, that's not going to be a chain isomer. They are actually, okay, so this one here is a carboxylic. This is a carboxylic. And this one here is an ester. So when they have different homologous groups, then they are called functional isomers. This one here is a ketone. And this one here is an aldehyde. So they have a different, they are also functional isomers. This molecule here is an alcohol. And this molecule here is also an alcohol. Okay, so let's see the chain though. So if we look at this one, it's got 1, 2, 3, 4 carbons in the main chain. And this one has 1, 2, 3, 4 carbons in the main chain. So they are the same. So it's, they are not chain isomers. So I think we found the only chain isomers. Okay, now for functional isomers, these have to be different things. So for example, B and C are functional isomers because the ones are ester and the ones are carboxylic. And then D and E are also because the one is an aldehyde and the other one is a ketone. So we could say D plus E. Okay. And then positional isomers would be F and I. The reason is that the chain is the same, so it's not chain isomers. They're both alcohols, so that can't be functional, but it's the position of the alcohol that is different. Here you can see the OH is on carbon number 1. Here you can see the OH is on carbon number 2. So that position is different, so that's why they are called position isomers. In this question, we are going to compare the boiling point of pentane and butane. So step 1, let's go draw those out, okay? So pentane is 5, and it's just a normal alkane molecule with all these hydrogens. There would be 12 hydrogens. Kevin, how did you know there were 12 hydrogens so quickly, my bro? It's because of the general formula of pentane, or alkanes. It's CnH2n plus 2. So if I know the number of carbons, then to get the hydrogen, I just say times 2 plus 2. Okay, Kevin, too much. I've just woken up. Okay, sorry guys, sometimes I go on my own little rant. Yeah, okay. Maybe I've been indoors for too long. Okay, now what I would always suggest is draw another pentane molecule. Why? Well, when you boil something, you are separating the molecules from each other. So you are going to be separating these two molecules from each other. You're not going to be breaking these bonds over here. That's not what we do when we boil something, okay? Now, on the other side, let's go draw butane. And of course, we can draw 2 of them because you're going to be separating the butanes from each other. Kevin, aren't we separating pentane from butane? No, that's not what these questions mean. They mean if you had a container filled with pentane, so this would be a container filled with pentane, so there would be millions and trillions of pentane molecules, and then on the right here you would have a container filled with butane. Okay, that's what these questions mean. Okay, so butane just has 4. Okay, so what we do when comparing boiling points, okay, for 4 marks, what you want to do, step 1, or let me first explain everything to you guys in a simplified way, and then I'll show you how to write the answer down to get all the marks. So let me show you the basics. What you should understand is that this pentane, or these pentane molecules, they are alkanes. Now, alkanes are non-polar, okay? They're not polar, they are non-polar. So the only intermolecular force, we could talk about dipole-dipole, London, hydrogen. hydrogen bonding, sorry. So when you have non-polar molecules, the only intermolecular force that we have is London forces. That's going to be the same for these ones over here. So you might be thinking, well, okay, if there's London forces for both, then surely the boiling point is the same. But in fact, that's not true. What happens is the following, is that, I'm going to make this really simplified. You could imagine that there's like a London force over there, then a London force over there, or like this area, this area, this area, this area, and this area. So you see that there were 5. I'm not saying this is exactly how it is in real life. I'm just trying to make this very simplified for you. And then here there's only 4 like attachment areas. So when you have a longer molecule, the London forces, you can almost add them together to see what the total London force power is, okay? So the longer the molecule, the larger the overall London force effect becomes, and it becomes more difficult to separate these 2 molecules from each other compared to if you wanted to separate these 2 from each other. These 2 will be easier to separate than these 2, okay? So these 2 are more difficult because they hold on to each other a little bit stronger because there's more London forces that are busy working. So to boil this one, remember what boiling means? It means that you are turning a liquid into a gas. So you are separating the liquid molecules from each other and turning them into gas. So you are separating the molecules. So if you wanted to separate these 2, you are going to need to use more energy than if you wanted to separate these 2. This means that you would need a larger temperature, because remember, temperature is energy. So you would need a higher or a larger temperature to separate these 2 than if you wanted to separate these 2 molecules. Okay? Hope that makes sense. If you understand that, then that's brilliant. Now I'm going to show you how to write this in a more formal way in an exam. Okay. So if you don't mind, I'm going to quickly erase the bottom parts here. Actually, I erased everything, but you should remember everything we've spoken about. Okay, so what you do for 4 marks is, so here's like a little template that you can use. Mention the dominant intermolecular force in molecule 1. Mention the dominant intermolecular force in molecule 2. Then do like the comparison part, and then the conclusion. Okay, so what do I mean by that? So you start off, now here's where we're going to write our answer. So you're going to say pentane molecules, or pentane molecules contain London force intermolecular forces. Okay. You can then say butane. See, I'm not comparing them just yet. I'm just saying what they have. Butane molecules contain London force intermolecular forces. Then what we can say is that pentane is longer than butane. The larger surface area causes the London forces to be stronger than in butane. Maybe over here we should have said for pentane molecules. So what I'm trying to say is that the larger surface area for pentane molecules causes the London force to be stronger than in butane molecules. Now, here's the part where we do the conclusion, okay? So, sorry, I've run out of space, but the conclusion would be, therefore, more energy is needed to overcome the forces of attraction in pentane molecules. So we can say pentane has higher boiling point. Okay, so I hope that all made sense. This question wants us to compare the boiling point of pentane and pentan-2-ol. Okay, so what I would say is just draw two pentane molecules quickly. So pentane is just a normal 5-carbon alkane. I'm not going to go do all the hydrogens, but you know they're here, right? Okay, so there's that. Right, the reason I always draw two is because remember, when you are looking at boiling points, you are looking at the forces in between the molecules. So you're looking at these forces, you see, in between the molecules. You're not looking at the forces in the molecule. Those are called intra, but we're rather looking at intermolecular. Okay, so it always makes sense to draw two if you really want to get a good idea of what we're doing. Now let's go draw two pentan-2-ol molecules. Pentan-2-ol is an alcohol where you have an OH on carbon number 2, and then of course hydrogen everywhere else. Okay, but I'm not going to draw that, just to, we know. And then let's draw another one. This time I'll make the OH face upwards. Why not? And then let's do that, let's do that, let's do that, let's do that. Okay, perfect. We would be looking at these intermolecular forces between the molecule. Okay, so what we need to do, let me first explain this to you in a simplified way, and then we can write down the formal answer, like the way you would do it in a test. Okay, so in organic chemistry with molecules, and we started learning about this in grade 11, you know, you get different intermolecular forces. The three main ones that we use in grade 12 would be London forces, dipole-dipole, and then hydrogen bonding. Hydrogen bond. Okay, those are the three that we look at. Now, London forces are always going to be when you have an area of a molecule that is non-polar. Well, let me actually write it out better for you guys. You can make some notes. So London forces are always going to be for the non-polar part of the molecule. Your teacher might call it the alkyl part of the molecule. It's the CH part. It's all this CH area. In the alcohol, it's all of that over there, or like, for example, there. It's where all the C's and the carbons and the hydrogens, those are the non-polar alkyl parts, okay? What they're trying to say is alkane, but the YL is just, yeah, don't worry too much about that. Okay, then you get the dipole-dipole part. Now that's typically next to a polar, well, that's always by a polar part. Okay, that could, for example, be like a carbon double bond oxygen, or it's a polar part of the molecule. And then hydrogen bonding is also polar, but it's just a special type of polar. Okay, so it's just a special type of polar when you've got hydrogen bonded with nitrogen, oxygen, or fluorine. So dipole-dipole and hydrogen bonding, it's the same type of thing, but hydrogen bonding just has its own unique name because it's a bit stronger. So scientists were like, okay, it's a little bit stronger, so let's just give it its own special name. But it's actually also just a polar type of thing. Okay, so what we would now do is you would look at these molecules here, and you would realize that there's only carbon, hydrogen in that one. So these molecules only have London forces. They don't have, why does it keep doing that? They don't have hydrogen bonding or dipole-dipole. So these molecules only have London. London forces are very weak. Okay, in this molecule over here, you've actually got a little bit of everything. And I'm going to put this into formal writing soon, but I'm just explaining it to you guys. So here between these parts over here, you see those are just carbon-hydrogen parts. So that's where you would have your London forces over there. Then you've also got the OH part. So wherever you have hydrogen bonded to either nitrogen, oxygen, or fluorine, there's hydrogen bonding. So we've also got some hydrogen bonding taking place over there. But then we also have dipole-dipole. Because here you've got a carbon-oxygen, and here you've got a carbon-oxygen, for example, and those parts are both polar, but they're not hydrogen bonding, so that's where you would get the whole dipole-dipole. So the way that we can now go put this into words for 4 marks is the following. So what you do is you just take the first molecule, and you just mention what type of intermolecular forces it has. So you can say pentane contains London forces between its molecules. Okay. Then you just, what you do next is you just say what the other molecule has. You're not comparing them just yet. You're just saying what they have. You could say pentan 2-ol contains London forces. Some teachers will only ask you to mention the most dominant one, the strongest one. But I'm rather just going to give you the whole spectrum, okay? So you can take from it what you want. So some teachers would only mention the hydrogen bonding, but I'm just going to mention everything. So we could say pentan 2-ol contains London forces between the alkyl parts, dipole forces between the permanent dipoles of the carbon-oxygen and oxygen-hydrogen bond. Okay? Then we can say, and then it also contains, and this is the most important one, hydrogen bonding between the OH groups. Some teachers will call that the hydroxyl groups. Okay, so alcohols actually have all 3. They've got the London, they've got dipole-dipole, and they've got hydrogen bonding. Okay, now we need to summarize. That's where you get your 4th mark. So, actually, sorry, we've only done 2. So what we did is we said, what does the first molecule have? That's step 1. What did we say for the second molecule? Step 2. Step 3, we can say that hydrogen bonding and dipole-dipole forces are stronger than London forces. Then your 4th step is to make a conclusion. This is where you actually answer the question. So I'm going to put my 4th one up here. But don't say 1, 2, 3, and 4 in the test. I'm just showing you the 4th case. So the next part would be, therefore, more energy will be needed. You see, because the forces between the alcohol molecules are much stronger, so you would need more energy to separate them. Okay? So you're saying more energy will be needed to overcome the forces of attraction in pentan 2-ol. Therefore, pentan 2-ol has the larger boiling point. This question wants us to compare the boiling point of butane with butanoic acid. So what I would always say is draw 2 butane molecules. So that's just a 4-carbon with hydrogens, of course. Draw another one, because remember, when you are looking at intermolecular forces, you are looking at the forces needed to separate these molecules from each other. Okay? You're not trying to break those bonds. That's not what we're doing when we boil something. So there's butane. And now let me do butanoic acid. So that's going to be one little container. You can imagine like a big container filled with millions of those molecules. Now we're going to quickly look at butanoic acid. So I always like to draw 2 of them. You can draw 55 if you wanted to. Might just take a lot of time. Let's draw that a little bit better. So we know that it's got that. Let's actually draw it upside down. And then this one I'll draw the normal way, just so we can have a look at it. We can have a look quite nicely. Okay, so there's 2 butanoic acid molecules, and of course there's going to be hydrogens everywhere. Okay, and I should go put those all in, but I'm just saving some time. You guys know about that. So there are 3 main intermolecular forces that we look at. That is London forces, and that is whenever you have non-polar parts, non-polar, which is pretty much when you have hydrogens and carbons. So for example, this part here is a non-polar part. This is a non-polar. That's of course non-polar. That's non-polar. So it's any part that has carbon and hydrogen, pretty much. That is your non-polar part. Okay. Then you get dipole-dipole, which is where you have something like a carbon connected to an oxygen or a double bond oxygen. Those are all dipole-dipole parts. And even oxygen connected to hydrogen. I know that that's also hydrogen bonding, but it's technically also dipole-dipole, okay? Because that's a polar part. Now, hydrogen bonding, the strongest, is specifically when you have hydrogen connected to either nitrogen, oxygen, or fluorine. Okay, so let me explain to you guys the basics of how we can see which of these has a higher boiling point, and then I'll show you what to write in a test. So can you see that this molecule here is completely, it's only carbon and hydrogen, okay? So that's non-polar. So the only intermolecular force that you are going to see here is going to be London forces. Now, London forces are the weakest forces that we get for intermolecular forces, okay? If you come down to butanoic acid, it's got different things. This part here is exactly the same as the butanoic acid. This part here is only going to have London forces, okay? Because that part there is carbons and hydrogens only. Then if you look here, you see how we're getting these like carbon double bond bonds, for example? That's going to be, and even over here, you see there's a carbon bonded to an oxygen, which is like that. All of those areas, that's all just dipole-dipole. Okay? And then, when you've got your whoops, let me get a better color. So when you've got OHs like that, then in between there, you're going to get some hydrogen bonding. And over here, this blue part, that was your dipole-dipole. So you see that carboxylic acids have a little bit of everything. So the forces in between the carboxylic acid will end up being much stronger than the forces in between the butane. So it will be more difficult to separate butanoic acid molecules from each other. So we would expect that the boiling point is going to be much higher for butanoic acid because more energy is required. Okay, so let's go put that into a formal writing now. So what you do is you break it up into 4 steps. Step 1, just take the first molecule, which is butane, and just mention what type of intermolecular forces you can see. So we could say butane contains London forces between its molecules. Okay, we could then say that butanoic acid contains London forces between the alkyl, which is the carbon-hydrogen parts, sections. Then we could say it's got dipole forces. Some teachers wouldn't expect you to give all of these. They would only expect you to mention the most dominant ones. So they would only expect you to mention the hydrogen bonding. Okay? So if your teacher does that, then fine. I'm just giving you the most complete answer so that you have the fullest and deepest understanding. Okay? So dipole forces, it contains dipole forces between the permanent dipoles of CO bonds, C double bond oxygen, and even the OH bonds, okay? And then we could say that it's got hydrogen bonding between the OH, or your teacher might call it the hydroxyl. That's what OH means, hydroxyl sections. Okay, and your teacher might call this the carbonyl section, for example. So every single school is different, and so I'm not going to give you like one answer and expect that, but what I'm teaching you is understanding so that you can adapt to whatever your teacher's saying, but you'll have a much deeper understanding of what they mean. Okay, now we've done 2 steps. You need to come up with 4. So for the third one, you just you make like a comparison. So you can say that dipole forces and hydrogen bonding is stronger than London forces. Step 4 is where you make your conclusion. You say, therefore, more energy will be needed. I'm really going to run out of space here. Needed to overcome the forces of attraction in butanoic acid. Okay, now we need to add a little extra part. So I'm going to erase all of this, if you don't mind. Let's carry on here. Therefore, butanoic acid will have a larger boiling point than butanoic acid will have a larger boiling point than butane. Classify the following reaction as addition, elimination, substitution, esterification, or combustion. Okay, so let's try to see what's happening here. So, of course that could just be like, okay, see how you have this plus this, and now it's forming one thing, so that's going to be called addition. But I actually want to explain exactly what's happening here. So, you see what happens here is that we've got a double bond. Okay, now what double bonds love to do is double bonds love to break. Okay, so they break the double bond, and then what that allows is that, you see, because carbon always has to be surrounded by 4 things. So this carbon has 1, 2, 3, 4. Okay, and this carbon also has 1, 2, 3, 4. So if we break that double bond, let me actually break it by taking that out. Whoopsie, let's take that out. Okay, you see now what happens is that each of those carbons now has 3 things. So that double bond that broke up we can rather break it up and then rather add a little attachment or bond over here. So we can add a bond over there, and we can add a bond over there. What then happens is that the H is going to go somewhere, and the Cl is going to go somewhere else. Now, according to Markovnikov's rule, this is where you have to follow the riddle of the rich get richer, and then the poorer get poorer. And remember that when we talk about this riddle, we are talking about hydrogen, okay? And this part's not relevant. That's only when we do elimination. When you do addition, which is when you are adding molecules onto this molecule, that's called addition. You're adding things onto the molecule. So this H is going to go to the carbon. It says that the rich get richer. So the carbon that already has the most hydrogen is going to get another hydrogen because the rich get richer. So here's a carbon with 2 hydrogens, whereas this carbon only has 1. Some of you might be saying, yeah, but Kevin, bro, listen up. This carbon has 3. But we're not looking at that carbon. You're only allowed to look at the 2 carbons that were next to the double bond. Okay? So those are your only 2 options. So that means that this hydrogen over here is going to add on over there. Okay? And then the Cl is going to go to the other place. And that is how we can see there's a Cl over here and there is an H. So I wanted to just give you a bit of a background about what's actually happening there. But the idea is that you are adding these 2 elements onto the molecule. So this is called addition. Okay? That is going to be called addition. Classify the following as addition, elimination, substitution, esterification, or combustion. Okay, so let's see what's happening here. So what actually happens is that, can you see over here we have a Cl, okay? And then in the product, all that's happened is that that is changed to an OH, okay? And you see this is H2O, so it's actually H. You can think of it as OH. Okay, so what happens is that this OH replaces the Cl, okay, and then the Cl replaces that OH. So you see how we end up with a product that has HCl, and then the OH has landed up over there. So all that has happened here is we've just done a complete switch. We've added the OH over here, but then we've also taken the Cl away. So we added and we took away. When you add and you take away like that, then that is not going to be called addition or elimination. That is just substitution. It's like when you're playing rugby or soccer or hockey or netball. I'm in Thailand at the moment, and volleyball on the beach is quite popular here. But all these different type of sports, when someone gets injured, what typically happens is that someone comes off the field and then someone goes back onto the field. That is called a sub or a substitution. Okay, so this reaction is a substitution. They've literally just changed the one molecule for the other, or they've made like a swap or a switch. Okay, classify the following reaction as addition, elimination, substitution, esterification, or combustion. So what's happened here in this reaction is, okay, you see we start off with this molecule. Now, in the product, there's a double bond. What that means is that we have lost certain things. So can you see over here, for example, we've lost that. So that means we lost this one over here. Okay. And you can see over here something's missing. So we've lost that as well. And that would be this OH. So what happened was that the H and the OH get removed. And they would probably join together to become water. That's why we can see water in the product. And, okay. So if you eliminate the OH, if you take that away, and then you take away this H, then you see the problem is that, it's difficult to write with a white pen on a white screen. I can't even see where my pen is. Oh, there. Okay. So you see the problem there is that you now have only 3 bonds over here and only 3 bonds over there. So the way that you would fix that is by putting a double bond. And that's what we can see happening over there. Okay, so let's quickly go back and just quickly try to finish this up. So what I'm trying to tell you guys is that we took the H and the OH and we took it away from the molecule. So we eliminated those 2. We didn't add anything back. We didn't like swap this for something else. We actually eliminated. So this reaction is a elimination reaction. Classify the following as addition, elimination, substitution, esterification, or combustion. Okay, so on the left here, this is an alcohol. And over here we've got the C double bond oxygen with an OH. That is a carboxylic acid. Now, we should know that when you react an alcohol and a carboxylic acid, you produce an ester. So this is going to be esterification. This reaction is esterification. There is another name for it that some of you might want to use, and that is condensation. You can use that as well. For this question, we have to give the reaction conditions. So that's quite interesting. We need to mention things like temperature, catalyst, all of those weird things that that we've learnt about for different reaction conditions, okay? Now, your textbook might say slightly different things to what I'm going to be saying. Your teacher might say slightly different things, but I'm just going to give as much as I can, and then you can just take from it what you want, okay? Like, even in the final examinations, they sometimes don't expect you to say everything, but I'm just going to try to be as thorough as possible, and then you can just adapt to what your teacher is saying and things like that. Okay, so we need to try and get an idea of what's happening here. So here we have an alkene. Okay, and what happens is that we are adding this HCl to the alkene. So maybe this hydrogen here would end up going over there, and then the Cl would be going over there, and that's how we can see the product. Okay, so this is an alkene being converted into a haloalkane. So when you're studying at home, you should just know alkene going to haloalkane, and then you should just try to have your reaction conditions for that one. There's about 12, I would say 12 reactions that we have in total, and you just need to memorize the reaction conditions, okay? So for this one, it is typically, we don't want to have any water present. So we'll just say that the dry... Okay, now sometimes another word for dry is anhydrous. So your teacher might use that word. Anhydrous means no water present. So you take the dry HCl and you add it directly to the alkene. So you say added directly to the alkene. So you just add these two things together, okay? There's no other real special conditions. There's no catalyst. You don't need to use special heating techniques. You're just going to add them together. Okay, so that's one of the easier ones. Here you need to give the reaction condition for this reaction. So you need to memorize the reaction conditions. So there's probably 12 different reactions you need to know. So the way I would do it is I would have like my notes in one of my little books that I make notes in. And all I would do is the following. I would identify what is this and what is this. So not the name, but just the homologous. So I know that this is a haloalkane. And it's converting into an alcohol. Okay, so you should then have notes on how do you take a haloalkane and you convert it to an alcohol. So haloalkanes are the ones that get students the most, because this is the one, it's the haloalkanes where you can sometimes use concentrated base to turn it into elimination reaction, or you can use a dilute base and then that turns it into a substitution reaction. Okay, now this one's a little bit more interesting though, because we're using water. Normally we would use NaOH or KOH. When we are using water, that is like we typically call that one hydrolysis. Okay, so in this one, because we're not using KOH, which is a base, or NaOH, which is a base, you're not going to say in the reaction conditions that you're going to add a dilute base, because we're not adding a dilute base. What we are going to do is we're going to add excess water. We're going to heat the reaction, but not strongly, just moderately. We typically only use strong heating when we're doing elimination reactions. This is not elimination, this is just a substitution reaction, okay? And then another one, now, you might just see if your teacher is very strict about this one. Sometimes they don't really expect you to remember this one, but one of them is that you dissolve the haloalkane, which is this one, dissolve the haloalkane in ethanol. Okay, so those are three different reaction conditions that we typically use. We dissolve the haloalkane in ethanol. Okay, so that's this one over here. We add excess water because we need water, of course, and then we just heat the reaction moderately, which is like average. We're not going to heat it up strongly. That's typically only when we use elimination. Give the reaction condition for the following. Okay, so for reaction conditions, I know it can be a bit overwhelming, right? Like remembering all these different things like catalysts and platinum, palladium, and all these weird things, okay? But there's only really like 12 reactions that we need to memorize. So what I would do is I would first ask you to identify what is this? Like, is it an ester, carboxylic acid, alcohol, alkane? Well, you see it's got this, so this is an alcohol. Okay. And then it's going to an alkene. Okay. So then you should have notes that you've made or whatever that give you the reaction conditions for alcohol going to an alkene. That's how you should do this. And then if you just go over that a few times, it's only 12 different reactions. And then once you know it, it's perfect. Okay. So alcohol going to alkene, we know that that is elimination. Okay. We can see that this is being taken away. You see it's not here anymore. And then this wait, what else was taken away? Oh, this hydrogen was taken away. You can see it's not here anymore. Okay, so they are eliminating. Now, whenever there's elimination, we're typically going to use strong heat. Okay, strong heat. So that's the first reaction condition, I would say. Strong, or heat strongly, sorry. That's the way they do it. Heat strongly. Now, typically, whenever we have an OH involved, or like an alcohol, sorry, as soon as there's an alcohol involved, we're typically going to use a H2SO4 catalyst. There are other catalysts you can use. I think the other one is H3PO4, something like that. Your teacher might use that one, but I typically just use H2SO4. And we're supposed to say that it is concentrated. H2SO4 catalyst. It's a catalyst. That's why you don't see it over here. So that's it for this one. But I want to just remind you, whenever there's elimination, then we typically use strong heating. What that means is like heat it quite aggressively. Give the reaction conditions for this reaction. Okay, so what we have here is we have an alcohol. All right, let's just say alcohol. And then here we can see there's a carbon double bond oxygen with an OH. That's a carboxylic acid. So can you remember what type of reaction it is when you're going from an alcohol? Were you adding an alcohol and a carboxylic acid? Well then if you remember that this is esterification. You see how we're producing an ester. So in your notes that you make, you should already know your reaction conditions for esterification. I recommend you just try to memorize these reaction conditions because there's quite a lot of them, or there's 12 reactions that we really look at. And if you can just memorize it, then it just makes your life so much better. So esterification, what we will use is we'll use a concentrated catalyst, and that would typically be H2SO4, sulfuric acid. And then we also need to use heat. Now, it doesn't have to be like a strong heat, but it's more like a moderate type of heat, okay? But the idea is that we do need a bit of heat for this reaction. So it's two things. We need the catalyst with H2SO4, and then we need to use heat. Here we need to come up with the reaction conditions needed for this reaction. So you need to identify what's happening, or what we're doing. So we're going from an alkane, and we're converting it to a haloalkane. Okay, so if you look in your notes or whatever, you should have a reaction condition for alkane going to haloalkane. And what you should realize or see is that this is the reaction where you can either use UV, so like the sun's energy, so UV light, or if you don't have access to UV light, then you could also use high temperatures, like heat. So you don't have to use UV light and heat. You could just say UV light or heat. Because sometimes you don't have access to UV light, then you could just use heat to get the same effect. What we're going to do here is we are just going to look at this reaction diagram that they've given us. So for the first question, it says classify reaction A as elimination, addition, or substitution. So have a look what happens here. At the starting point over here, we have an alkene. Now, you've maybe heard me say this cringy thing before, but alkenes are keen to react. So what I mean by that is that they love having things being added on to them. And so what we can see is that what happens is that this double bond breaks, and then you open up two extra spaces. And then can you see that we've put an OH in this position over here, and then we've put a hydrogen in this position over here. So what did we do to this molecule? Did we take things away or did we add things? Well, we added things, so that is a addition reaction. For question, or for the next one, it says classify reaction B. Okay, so B is going from the alkene down to here. So once again, we've added a Cl over here, and then we've added a hydrogen over here. So that would also be addition. Okay, so what we're going to do here is we are going to examine this reaction diagram, and then we've got 3 questions over here. So for the first question, it says, is reaction A hydrohalogenation, hydration, halogenation, or hydrogenation? So those are all the different addition reactions that we've learnt about. So for reaction A, what are we adding to this molecule? Well, we're adding an OH over here, and then we're adding a hydrogen over here. So we are adding an OH and a H. That is adding water. So that is when you add water to your body, you are hydrating. So this is a hydration reaction. So let's say a hydration. Okay. And the next one, this one over here. So is reaction B. So they want us to look at reaction B. Okay. So what are we adding? Well, we're adding a Cl, see it there? And then we're adding a hydrogen over there. So we're adding a hydrogen and a halogen. So we are adding a hydrogen and a halogen. So this is hydro. I'm just going to circle it. It's hydrohalogenation. And then the last one is reaction C. So reaction C. So let's see what we're adding. So we're adding a hydrogen and another hydrogen. So that would be hydrogenation. So what we're going to do here is we are going to examine this reaction diagram. So for the first question, it says, give the reaction condition for reaction A. So when it comes to reaction conditions, I know, guys, it's not the best, but there are mainly 12 reactions that we need to know in grade 12, and you just need to memorize these reaction conditions. So the way that you do it is the following. They said it's for reaction A. So what you do is you look at the starting material, and what is it? It's an alkene. What is the final product? It is an alcohol. Okay, so you then need to have some notes that you've already made, I hope, where you have reaction conditions when you go from an alkene to an alcohol. Okay, there's only 12 different types. So when you go from an alkene to an alcohol, you need to make sure that there is excess water. So you need a lot of water. You are going to use a strong catalyst, and that is usually H2SO4, which is sulfuric acid. And then we don't need to use strong heat or anything like that. Strong heat, or like heating it up really strongly, is usually something we do when there's an elimination reaction. But this is an addition reaction, okay? So those are the only 2 reaction conditions that we would say for that first question, okay? So for that one over there. Moving on to the second question now. So we need to give the reaction conditions for B. So for B, you're going from an alkene to a haloalkane. So in your notes, you need to have a reaction condition for alkene going to a haloalkane. And what you should have there is that there should be no water present. So you're just going to add, the dry HCl, or so you can say add the dry HCl. Some teachers, instead of using the word dry, they might use the word anhydrous. It means no water. Add the dry HCl to the alkene.